All right, the last thing we're going to tackle in this, I know this has been a kind of a longer section, but last thing we're going to tackle here is the Bezout's identity for polynomial rings. So what should it say? Well, again, everything that we're doing in this last part of the section requires a field. Then for any f and g in f adjoint x, of course, not both 0, there exists polynomials. Let me say p and p of x, I'm just going to say p and q, actually, such that pf plus qg is the GCD of f and g. And the proof of this is exactly the same as in z. So you go in, you run the Euclidean algorithm. So this is written out pretty explicitly in the book. Just for this video, I'm just going to say it's the same as in z. You run the Euclidean algorithm. You solve for remainders. And you do repeated substitution until you have the equation. Right. So I think this is best illustrated with examples. So let's do that. So here's the example from the last video, the very last example. And we ran the Euclidean algorithm. We found the GCD is 1. So that's our step 1. Step 2 is solve for remainders. So we take this and we say, okay, x to the 5th plus x to the 4th plus 1. That's our f. And then subtraction is really a multiplication by 2 over f3. That's what we're doing here, f3. So I'm going to, instead of subtracting over, I'm going to move over but multiply by 2. It's the same as subtraction. You could write subtraction if you wanted. And that's equal to our first remainder, r0. Okay, so I just took that first equation, solved for r0. And we'll take our other equation, and we're going to solve for r1. Okay, so we have x cubed plus x, and then we're going to subtract that over, that is, add twice it over. And that's equal to 1. And then what we're going to do is we're going to take this guy here, and we're going to plug in it into here. That is, we're going to plug in what it's equal to into there. So let's do that. So on the one hand, we have 1, which is the GCD, of course. On the other hand, let's see, we're going to get x cubed plus x is going to stay. And then we have twice 2x plus 2, which is really 4x plus 4, which is really x plus 1, but leave it as it is. And then we're going to plug in this whole left-hand side now. So we have x to the 5th plus x to the 4th plus 1 plus 2x squared plus x plus 2, and then x cubed plus x. Whew. All right, cool. Now we don't want to multiply this out. We want to keep the fact that this is an f and this is a g. We want to keep those there. So in fact, what I'm going to do is I'm going to go in and rewrite this where I'm just going to write g in place of that. Let's do this arithmetic here. Twice 2x plus 2 is 4x plus 4, but 4 is the same as 1 mod 3. So this is really x plus 1. And then it's going to be f plus, all right, this is 2x squared plus 2x plus 4, but 4 is the same as 1. And then we have a g. And that just looks so much nicer. All right, so now what do we have here? Well, we can multiply this through, and what we should get is x plus 1 times f plus x plus 1 times 2x squared plus 2x plus 1 times g is 1. And then lastly, we can combine the g's. So we have x plus 1 times f plus whatever this is. Kind of a lot to keep track of. But nevertheless, we have that. And let's see, I worked this ladder guy out in the notes, and it looks like let's see, what did I find? Ah, yes. So it looks like I found that this ladder guy is equal to 2x cubed plus x squared plus 2. All right. So this is the same thing that we did when we learned Bezout's identity for the integers. However, we just have some slightly more complicated division now. These coefficient polynomials are still called Bezout coefficients. And so we found the Bezout coefficients here. And again, it's the same thing that we did with the integers. You run the Euclidean algorithm, you solve for the remainders, and you substitute in. And you eventually will get the GCD on one side and something times f plus something times g on the other side.